Alright, hey y'all, it's Miss Summers with some notes on theory of plate tectonics. So in these notes, we are going to look at the evidence that supports the theory of plate tectonics that states that the tectonic plates are indeed moving around, just like our boy Alfred Wegener thought. Alright, so just a quick reminder of our friend Alfred Wegener. So he thought of continental drift. He had this big idea that all the continents used to be together in Pangea. He knew that because they fit together, like South America and Africa, and North America and Eurasia. They all kind of fit together like a puzzle. They had the matching fossils, the matching mountain ranges, and the climates that show, all right, Antarctica used to be a little warmer, Africa used to be a little colder, that type thing. Okay, so he knew the continents moved around, but he didn't know how. And that's what theory of plate tectonics states. All right, so let's start with defining what it is. So the theory of plate tectonics was proposed in 1965, which if you think about it, really wasn't that long ago. It was 55 years ago. Not very long at all. By this fellow named Tuzo Wilson. And he combined continental drift from Wegener and seafloor spreading, which was this guy named Harry Hess. We'll talk about that later. And he said that convection currents in the mantle move lithospheric plates. And that movement causes geologic activity, like building mountains, eruptions, and earthquakes. All right, so convection currents in the mantle move tectonic plates. All right, so let's look at how a convection current works. Whoops. So convection is the movement of heat through a medium like a fluid or gas. Generally, when we're talking about it, we're either talking about like water or air. But in this case, we're talking about that semi-solid stuff that's in the mantle. All right. So the bottom of the mantle, the lower mantle, is hotter than the upper mantle because it's next to the core. So it heats up down here. Imagine like a pot of water on the stove. All right, the bottom gets hotter first. Because it's hotter here, the material at the bottom will expand, and that makes it less dense. Then it rises. All right, just like hot water would rise or hot air would rise, the hot material in the lower mantle rises because it's less dense, because it's heated up. Well, now it's at the top of the mantle. It's near the asthenosphere. Remember, that's right below the crust. And it's not near the heat source anymore, so it cools back down. When things cool down, they contract or get smaller, and it becomes more dense, and it sinks. And it goes around in a circle, like this. So you have a bunch of these convection currents happening in the mantle. All right, the constant rise and fall of magma and the material in the mantle causes convection currents that drives plate tectonics. All right, the crust is riding along these convection currents. Okay. So how do we know that that's a thing? How do we even know that the crust is broken up into different pieces? Well, our first piece of evidence is the Ring of Fire. The Ring of Fire is this line of active volcanoes. It starts at Tierra del Fuego, here at the tip of South America, goes all the way up the west coast, all the way up Central America, North America, around Alaska, down Japan and East Asia, into the Philippines, and it ends in New Zealand. All right, this line contains 75% of the world's active volcanoes, and something like 80% of the world's earthquakes happen on this Ring of Fire, okay? So earthquakes and volcanoes are happening at these plate boundaries. But sometimes they don't. All right, and that leads us to our next piece of evidence, which is called a hotspot. Hawaii is an example of a hotspot. Hawaii is in the middle of the Pacific plate. It is not near a plate boundary, but it's still volcanic. A hotspot is going to be this place in the mantle where magma comes up. Magma wells up at a hotspot, okay? As the plate moves over this hotspot, it will form a line of volcanoes, okay? So Hawaii is a chain of islands. It's an archipelago. All right. Kauai, which is the oldest of the Hawaiian Islands, is way over here. Well, millions of years ago, it used to be here above the hotspot. That's where it formed. As the plate moves, these older volcanoes get pushed farther away. All right? Eventually, Hawaii, the big island of Hawaii, it's over the hotspot right now. It'll move over where Maui is, and Maui will move over where Oahu is, and then there will be a new island over the hotspot. The hotspot is in the mantle, and it does not move. The plate moves over it. All right, so here's a little video, little animation of how a hotspot works. So here's the hotspot in the mantle. The plate is moving, but the hotspot isn't. All right. So each of these are new volcanoes that are forming. There's the plate that's moving. And there's the Hawaiian Islands. Whoops. Here's another example, another way you could look at it. This is a demo with cocoa powder, and I think this is like some sort of oil. I don't know. But that's not what I wanted to do. They're going to take... So this represents the plate, the cocoa powder. And they're going to put some Alka-Seltzer into this, whatever mixture it is, and it's going to bubble. That's the hot spot. All right. So there's a volcano forming right there. All right. As the person moves the plate, all right, the plate moves over. Well, there's a new volcano. Here's the old one. The hot spot is staying in the same spot. All right. That's a hot spot. That's how you get volcanoes not on a plate boundary. All right. So how else do we know that plates are moving? So we have the ring of fire. Most earthquakes and volcanoes happen at plate boundaries. We have our hot spots that show the movement of plates by making lines of volcanoes. There's 3 other pieces of evidence I want to look at. Our third piece of evidence is called paleomagnetism. All right. Paleo means ancient, and magnetism is referring to the polarity of the Earth's magnetic field. All you need to know for this, friends, is when new crust is formed at those divergent boundaries, all right, the minerals in the rocks, they line up with the magnetic field. Okay, they're going to say they're going to say north is that way or north is reverse. What happens over time, this is what I need y'all to understand for this. As the seafloor spreads, you get symmetrical banding patterns. All right, so if I look on the left side of the ridge or the right side of the ridge, this is symmetrical. It's a mirror image. What has happened, okay, the new crust forms here. As these plates move apart, all right, these bands will grow further and further apart. So this red arrow used to be with this red arrow over here. This blue arrow used to be with this blue arrow over here. It all starts at the ridge and it moves away. So here's another good diagram. I like this because it's like a before, during, and after. All right, we have these yellow bands form. That represents normal magnetism. All right, they're spreading apart. So these bands used to be together. Now they're apart. They're still symmetrical, though. These red bands form together at the ridge. As it separates, because it's on a divergent boundary, they'll move apart, but it's still symmetrical. All right, our next piece of evidence is earthquake patterns. Shallow focus earthquakes tend to be in or next to ocean trenches, and as the ocean crust sinks further, it produces earthquakes with deep focuses. So what that looks like, it looks like this on a graph or a diagram. For one of your assignments, you had to look at a graph of subducting plates with earthquake depths. The earthquakes are always going to be on the plates. They're on the subducting plates. Okay, so they're not randomly distributed. So if I have this plate here, for instance, the red is the shallow earthquakes. I'm never going to have a shallow earthquake over here because that's not where the subducting plate is. Green, those are my deep earthquakes. Well, I'm never going to have a deep earthquake right here where the trench is because that's not where the plate is. It shows us the outline of the plate subducting. And our final piece of evidence, seafloor age. Gotta know this, guys. The youngest seafloor is always located at the ridge crest. So in this diagram, we have the Atlantic Ocean here. We have the Mid-Atlantic Ridge in pink, this kind of pinky color. All right, that's the youngest seafloor. As that ridge, okay, as the plates are pulling apart at that ridge, the older seafloor gets pushed out of the way. All right, but just like paleomagnetism, there's a symmetrical pattern. All right, so you've seen this diagram in your assignments. So we have the ridge. So this area where my mouse is, that is the youngest right here. Letter A and number 5, those are the oldest pieces because they are farthest away. A and 5 used to be together. They formed at the same time at this ridge, and they have been moving apart ever since. All right. B and 4 used to go together. 3 and C used to be together. So it's that nice symmetry. Okay? So that concludes the 5 pieces of evidence you need to know for theory of plate tectonics. The theory of plate tectonics states that convection currents in the mantle move tectonic plates, and that causes earthquakes, volcanoes, and mountain building. Our evidence, we have the ring of fire. All right, most earthquakes and volcanoes happen at plate boundaries. We have our hotspots in the mantle that form lines of volcanoes in the middle of a tectonic plate as the plate moves over it. We have our paleomagnetism and our seafloor age. So you get symmetrical patterns of the magnetic banding or the age away from the ridge. And you have our earthquake patterns. All right, the earthquakes outline the subducting plates.